Hi everyone. In this video, I'll introduce our work IDFace, face template protection for efficient and secure identification. As face recognition becomes widely used in airports, phones, and access control, protecting users' face templates is crucial. This work is a collaboration between Hanyang University and Cryptolab. We propose a novel method that allows large-scale face identification to be performed securely even when all templates are encrypted with only a small computational overhead. Let's start by looking at why this problem matters. Traditional face recognition systems are fast and accurate, but they are vulnerable to reconstruction attacks. That means, if someone steals your stored template, they might actually reconstruct your face image. So we need a system that protects templates while still allowing similarity comparison. Homomorphic encryption provides this ability. It allows computation directly on encrypted data. In other words, we can match faces securely without ever decrypting them. This is the starting point of our research. When using homomorphic encryption, security depends on how we manage the encryption keys. So, in our setting, the system has two separate servers. A local server that stores encrypted templates and a key server that holds the secret key. This separation means that even if the local database is leaked, attackers can't recover any biometric information. The key server itself is assumed to be protected in a secure environment. For example, inside a trusted execution environment or a physically isolated module, which is realistic in large-scale face recognition systems. We also follow ISO standards for biometric protection, ensuring irreversibility, revocability, and unlinkability. In short, we make sure stolen data can't be reused or linked back to the user. Several previous studies tried to apply homomorphic encryption to face identification. They introduced clever tricks like rotation-based optimization and SIMD, single instruction, multiple data, parallelization to reduce computation. However, even with those improvements, large-scale identification, say, a database of 1 million faces, still takes several seconds to minutes, depending on the setup. Our goal was to make it truly practical. For instance, the best prior work, called HERS, required about 12 seconds for identification with reduced dimension templates, or up to 49 seconds with full dimension ones. We wanted to push that down to around 0.1 seconds, and that's exactly what IDFace achieves. Our method builds on the HERS framework and keeps its strengths, such as avoiding rotation and using only simple scalar multiplications, but we introduced two new ideas that drastically boost efficiency. You can think of IDFace as an upgraded version of HERS that redefines how templates are represented and encoded. With these improvements, the inner product, the core operation for matching, becomes dramatically faster. Here's our first key idea, the almost isometric transformation. We convert each real-valued face template into a ternary vector of only -1, 0, 1. This keeps the distance relationship mostly intact, but removes the need for expensive multiplications. Essentially, we just check the signs of the top alpha components of template, positive or negative, and perform lookups instead of multiplications. This transformation alone cuts the cost of the inner product calculation by a huge margin. Our second idea is the space-efficient encoding. Homomorphic encryption schemes, like Palir or CKKS, use very large message slots, much larger than needed for face features. So we pack many transformed templates together into a single ciphertext, making full use of the space. By separating positive and negative parts, we avoid overflow and still perform efficient single instruction, multiple data operations. This design allows us to search through massive encrypted databases very quickly. By combining these two ideas, we propose IDFace, a plug-and-play encrypted face identification scheme. It achieves between 16 times and 92 times speedup compared to previous state-of-the-art methods, while maintaining strong security. On a database of 1 million identities, IDFace identifies a person in just about 0.13 seconds, roughly twice as slow as plain unencrypted matching, 0.07 seconds. In other words, it adds only a tiny 2 times overhead yet keeps all computations fully encrypted. This makes secure face identification not only practical, but nearly as fast as unprotected systems. Next, let's look at the accuracy. We evaluated IDFace on 4 well-known benchmarks, LFW, CFPFP, HDB, and IJBC. Across all datasets, the accuracy drop was less than 2.5 percentage points compared to the plain model. This proves that our transformation and encoding preserve the discriminative power of modern face recognition systems, even under encryption. So we achieve both security and performance at the same time. To summarize, IDFace tackles the privacy risks in face recognition by enabling secure template matching under homomorphic encryption. Thanks to our two core techniques, the almost isometric transformation and space-efficient encoding, we cut the computation cost dramatically. Compared to previous HE-based methods, IDFace is up to 92 times faster, and its runtime is just twice that of a plain system. This shows that encrypted, privacy-preserving, large-scale face identification is finally as practical as it is secure. Thank you for watching, and feel free to visit our poster for more details.